Okay, the handout. So we introduced this reaction at the end last time. This might be the expected product. We expect the cation to be here, yeah. Secondary, this bromide adds to the cation, we'd end up with that product. In this case, however, this is the major product. What's going on here? How's this formed? That's a carbo-cation rearrangement. Let's look at this mechanism. It starts with the usual, H+. Just show this ionic. Okay? Alkene attacks H+. It's going to, these electrons move away, hinge out. Okay? We'll pull away and attack. Alright, that arrow right there needs to be very precise. Electrons are being pulled away from the bottom carbon, and they're going to bond to the H. The top carbon is bonded to the H. That gives top carbon bonded to the H as the electrons moved out, leaving this without a bond. That's a positive charge. Same step as before. The only thing we've done this far is reacted alkenes with H+. Okay? Alright, here. How could you get minor product as shown? Br minus then attacks cations. That would give that product. Right? There is a new H there. It's just not drawn in over there. But how do we get the other product? You can kind of back up here a little bit and say, we really need that carbocation. If we had that carbocation, could we then get that major product? Br minus adds to that carbocation. But we have this carbocation. Again, the H looks funny to me. It looks very funny. I'd rather not draw it in. It's a carbon with a methyl. Carbon with a methyl. Yeah, there's a new H there still, because the original one only had 2 there. There's 3 here. You got to understand that I'm drawing it in sometimes, but not all the time. I usually draw it in when we just first add it. Okay? So how does the cation end up here? It's a rearrangement, carbo-cation rearrangement. All right, what does the mechanism arrow show? Movement of what? Electrons. It does not show movement of atoms. It does not show movement of charges. It shows movement of electrons. All right. How many H's on this carbon right here? 1. 1 to begin. 1 still there. How many on the carbon now? 2. There's 2 H's there. How many H's on this carbon here? 1. 1 there, 1 there. How many here?
0.
If it was 1, it would not be a positive charge. The only way for that to be a positive charge is there to be no H there. No H there. We've got 1 here. There's none here. It's like we lost an H here, and we gained 1 over here. What happened is, one of these hydrogens here, all right, now I could draw it in like this with the H. I'm going to draw it in like this. One of these hydrogens moves over here. What happens is these 2 electrons here break away from this carbon and they move over here. All right? The line is 2 electrons. The line is a 2-electron covalent bond. We're going to break these 2 electrons away from this carbon and go over there. What does that give? It gives that. You got to know where H's are. Okay? You got to sit down and see where the H's are. If you can't do that, then you're going to have trouble with lots of things. All right? This is called a hydride shift, because the H move and the electrons. H and electrons. What would you call this here? First off, the charge would be minus, because H only supposed to have one. It's got two, minus. What do you call this? Hydride. Hydride. What do you call the Cl minus?
Chloride.
Bromine minus.
Bromide.
I, chloride, bromide, hydride. Yes. Hydride does exist. H and the two electrons shifted, so it's a hydride shift. And this is our mechanism. Okay? Why would this take place? What type of cation did we have here?
Secondary.
Secondary. When I say what type, I'm referring to primary, secondary, tertiary, right? What other type would you call it? The beautiful type? The cool type? Secondary. What type of cation is that?
Tertiary.
Tertiary. Did we go to a better cation?
Yeah.
Yes. Very often you get rearrangements to go to better cations. We call this a carbo-cation rearrangement. But careful, mechanistically we don't show the cation moving. Mechanistically we show what moving? The electrons moving. It's a mechanism error. The electrons moving. Okay, let's do this here. Here we go, we're bonded. Can we bond? All right, I'll bond this way. Next door is a carbocation. Your secondary carbocation. Okay? Are these electrons going to be attracted to that positive charge? Yes, physics. You need to take physics. You'll learn that positives like negatives. Okay. So here we go. You're a positive charge. These are electrons here, because I'm the nucleus, you're the nucleus, but the line is electrons. You think they're going to be attracted to you? A little bit. They're going to be, okay. There's always, all this is always going on. Okay? I'm going to come over and bond to you. I'm going to break free, okay? Now I can't take your whole arm. Right? Pretend like that I'm the bond. You just be the nucleus. Okay? These electrons just break free. Somebody pull my arm over there. You yank it over there. That's what we did. These electrons break free and they move over there and bond to you. Okay? Here we go. Move them over there. That's what we did here. Two electrons, we moved them over there. Sorry, I'm moving next door. Why? Secondary cation. I move next door and leave you as a what? Tertiary cation. You're better. You're more stable, tertiary cation. She needed some electrons more than you did. But she was secondary. You're a little bit more okay without them. You're okay? Tertiary is more stable. So the electrons go that way. This is okay? And this is known to happen. Carbocations are always prone to rearranging. One way they can rearrange, by a hydride shift. We'll see other ways they can rearrange. Now that we have a tertiary carbocation and we show the mechanism error for getting there, what's our next step? The Br minus was watching this, okay? Watching this. Now, the Br minus comes in and bam! Alright? Makes bond and then gives product, right? It don't matter how you draw these things around this carbon. It's a carbon with methyl bromine. Alright? Methyl, now the bromine is bonded. There's your mechanism. The major product comes from a hydride shift It comes from a carbo-cation rearrangement. Why major? Well, this reaction is known, and that's known to be the major product. Here's what we're going to do for us in class. Anytime you can rearrange to a better cation, always do that. And always let that be our major pathway, our major product. Okay? So if you were to see this reaction, you just say, I'm going to rearrange because that's what we said is going to be the major product. Does any of this form? Yeah, a little bit of this forms, but it's minor. Usually the question is going to say, show the major product of this reaction. What's the major product? The one that says major. Yes, that's the one you would show here. Does that mean other products are not formed at all? This is formed in less amount, minor. How could it be formed? Well, if this attacks here before it rearranges, okay? Before I rearrange, oh, bromine already attacked over there. Didn't have time to rearrange. Let me ask you this, and this applies going forward, okay? I talk about things that are going to be repeated. Which do you think would be faster, the hydride shift or bromide attacking here? And what's your argument? Which should be faster, bromide attacking here or hydride shift? Why hydride?
It's closer.
It's closer. It's internal. The hydride shift is going to be faster. The bromide is way over there, like 5 angstroms away. Might as well be 5 miles. This is right next door. Okay? Who can slap hands better? Okay? Who can slap hands better, me or you? I beat you, sorry. You didn't even hardly move. Boom, I just did it. Right next door. It's going to be faster. That's the argument for why the major product is going to be formed faster. The bromide doesn't have time to attack. You might wonder how this is formed at all. Okay, so there's some discussion of that. Reaction coordinate diagram. How many intermediates in this reaction? I did a complete mechanism. Every intermediate should be on the board. How many intermediates?
2.
2. A secondary cation, a tertiary. Which one's more stable?
Tertiary.
Tertiary. Could you plot a reaction coordinate diagram? Transition stage. What's the rate determining step here?
First one.
We said last time, typically all these reactions are first making the carbo-cation. High secondary, from there where are you going? You go down a little bit to a tertiary. See, from there you're falling back downhill, then you get to your neutral product. Okay, let's look at the one below. Now below we're doing a hydration with water and acid. Take this alkene and hydrate it with water and acid. Where are you going to make cation? Top or bottom?
Bottom.
Bottom, and then water adds. You lose a proton from oxygen, you get an OH here. Yeah. Uh-oh, that's a minor product. Major product, the OH ends up on what looks like maybe over here. Huh, what else?
Where's that other carbon go?
Total carbons, 1, 2, 3, 4, 5, 6. Total carbons, 1, 2, 3, 4, 5, 6. Something's going on here? Let's take it one step at a time. What's the first step of the mechanism? Because again, please read my notes on mechanisms, which is in one of the handout. Okay? Some important notes. A couple of warm-up questions. Okay, things to do, things to watch out for not doing. One thing it mentions is, whenever you do mechanism, you may not see every mechanistic step to get there at the beginning. We can kind of look at it and see, it looks like maybe something is done. But then go back and it's one step at a time. What's the first step here? Again, we've only done one first step, and it's an alkene reacting with H+. That's it. We've got H+ and alkene. We've never done anything different. Not yet. H+ and water. That's what we have here. This is going to attack, and okay, one step at a time. UH there, and positive here. Right? Regioselective. Now, if water added here, we can see how we can get this product. Then lose proton. But let's give mechanism for the major product, the one that's a little less intuitive. What do we need to do? Well, over here, we kind of need, you can't go over here and say, hey, we kind of need that cation. If we had that cation, would you be able to take it home from there? How can we get that cation? Move a methyl. We've got a carbon with 3 methyls. Now we've got a carbon with 2 methyls. The other carbon has 2 methyls. Where here, this carbon only has 1 methyl. See, that looks odd. That's a CH2, it's a CH3. In this case, one of the methyls moves over. Carbon, 3 H's there, and the 2 electrons. The 2 electrons break away. Okay? Here, I'm a methyl group now. I've got a carbon with 3 H's. The electrons break away and go over and bond next door. Okay? Somebody pull my arm over there. All right? That was your mechanism arrow. Yank these electrons over. What does that give? Well, it gives that. It does. Problem is that H looks funky up there. I mean, you can draw it in. There's a new H up here. But now this carbon has the methyl, and now it has another methyl. And we rearrange, this is another carbo-cation rearrangement. We went from secondary to what?
Tertiary.
Tertiary. Not by hydride shift. What shifted?
Alkyl.
Okay, it's a carbon. You might want to call this a carbide. Now just a hydride and chloride. Carbide is actually okay, it's just not used much. That's a carbanion. But for some reason that carbide is not hardly used. We just call this an alkyl. Because a methyl is an alkyl. And just call it an alkyl shift. By the way, I have seen written somewhere alkylide to indicate that it's an anion, sort of. But you don't see that much either. What's shifting? The CH3, right? This is all shifting, right? It's the CH3 plus the 2 electrons there. So if you just look at that part, it's like the carbanion is shifting. We just call it an alkyl in this case. Alkyl shift. You can get specific and call it a methyl shift. Alkyl being more generic. That gives that, right? Okay, you got to see this. You got to know where H's are. How many H's on that carbon over there? None, none, still none, because we've not magically gained an H. Since there's no H there, that's why it's a positive charge. Okay, how do we get home? We have water here. These electrons, say it with me. These electrons attack that. That gives what? O, Two H's are there, and that's a positive oxygen. And then how do we get the final product? Something has to take an H. What can take an H? What's the minus here? There's got to be a minus. You know, this is a generic way to show aqueous acid. But in practice, you've got to have some minus. Maybe it's HSO4 minus. That is, this is really sulfuric acid. And it's just shown ionized with water. Okay? We could use that. You can always also use water to take the H. These electrons take the H. These electrons move on to oxygen. That gives final product. And what did we form here, though? H3O plus. Catalyst. Hydration of alkene is acid catalyzed. Okay? We got acid here, right? And your acid is regenerated at the end. Either in the form of H3O plus, or you could have made sulfuric acid. Or other acids you could have used here. Okay? So that's another way to have a carbocation rearrangement. Alkyl shifts. Hydride shifts, alkyl shifts. Always be on the lookout for them. Over here, another type of carbocation rearrangement. These are also going to be alkyl shifts. But it's going to have a ring involved. Look at this reaction. You take this alkene here with a cyclobutane, treat it with HBr, we can get this product here, cyclopentane. A lot of times I'll write the size of the ring there just to clarify, make it very obvious. It's obvious anyway, but just as a confirmation. What's going on here? Obviously the ring has expanded. We call it a ring expansion. Is it an addition reaction? If you do formula, the formula of the thing on the right is the same formula plus HBr. Yeah, HBr has been added to whatever you begin with. Did we simply add it across the pi bond? No. Because if we had, yesterday we might have said product was maybe, where are you going to have bromine at for standard product? Maybe here. HBr adds across the pi bond without any rearrangement going on. Where are you going to make cation, top or bottom? Bottom, that's why I showed bromine here. Okay, that's a standard addition across the pi bond. This is not so standard. We've got a ring expansion going on as well. Okay? Mechanism. Well, the first step is the same step here. H plus Br minus, these electrons attack here. One step at a time. Methyl, boom, boom, H here, and cation here. We could step over here and say, what cation do we need? If we had that cation, would you be able to take it home from there? That's the cation we need. Can we get to that cation from this cation? We actually can. if you take these electrons here, okay, break them away from this carbon, just move them over there. That's the same thing we did before. Okay? Here we go. Somebody pull my arm over there. Grab it. There you go. That's your mechanism arrow. You want to pull these and pull them over there. Pull them over there. Now let's look at what that, I'm not going to draw it exactly like that. Let's draw it like this. Boom, 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 boom. We'll keep the H drawn in so it looks just like this. But instead of this here, it's now bonded here. Yeah? So this mechanism arrow led us to this. But hold on, where's charge at? Because you can't just charge.
On the left or here.
The charge should be where? The charge should be here because this lost a bond. It gained a bond. Charge is now here. It's the same thing. Okay? It just moved over. The only difference is this was a ring. Let's be a ring here. Okay? We're a three-membered ring. Or 5 or 4, whatever. But when I move over, okay? By the way, y'all are bonded too. Okay, here we go. We're a three-membered ring. When I move over, now we're a four-membered ring, because now you're part of the ring. That's what's going on here. All right? Move over, now this carbon's part of the ring. And now the ring is 5. Yeah? That's an alkyl shift. But it's more precisely called a ring expansion because it's not just a simple alkyl shift. This particular alkyl shift led to the expanding of the ring, and so we call it that. Okay, how do we get to the one on the right? How do we get here? We're already there. That is that. Yes, these are equal. Equal sign. Those are equal. That's the same thing, right? It's a 5-membered ring. 2 methyls. That's a CH3, that's a CH3. Again, with the H there, everybody see these are the same thing, right? It's a carbon with 3 H's and a carbon with 3 H's. 5-membered ring, 2 methyls, and a cation on one. It's the same thing. That's it. The hydride shift, not an alkyl shift, ring expansion gives this. Okay? Now, if you can see this, you don't have to draw this twice if you're doing it on a quiz or test, if you see it. I'm just trying to show you, help you see it if you don't. I mean, you don't even have to draw it like this. You can just work from here. This is it. Now what I need to do? These electrons then add here, and we're home. Right? Or you can do it over here. Either way, it's whichever way you want to do. You don't have to do it twice. These electrons add here, and we're home. And that's how you get this interesting product, which is now 5-membered cyclopentane.
Is the HBr reformed still?
Did the HBr reform?
Yeah. Or no?
Where did we reform HBr? No, HBr is not a catalyst. HBr is a reactant. It's reactive. Fully, you need a molar amount, stoichiometric amount. Okay, how about the one below? What's going on below? It's not a ring expansion, it's a ring contraction. Try that one on your own. It's going to be just the opposite. We got a big ring here, and when the shift takes place, we go to a smaller ring. It's just going the other way. Same basic principles, though. Sometimes things can rearrange multiple ways. I think there's a problem or two in the workbook that sort of ask you to consider all ways that a certain cation can rearrange. Okay, pink sheet, carbo-cation rearrangements. Did we take care of that? Yeah, we did those three? Roman numeral 5, ring-forming reactions. Ring-forming. Look at this reaction here. If you take this, it's got two alkenes. We call it diene. Take this diene reacted with HI, you can get the 6-membered ring over here. This is an addition reaction, because if you take the formula of that and add HI to it, then you have the formula for the product. But it's more than just a simple addition across a single pi bond. You obviously also have a ring formation going on. Okay, mechanism. Well, all we know so far to start is reacting with H+. We got two alkenes though. Which alkene do you want to react? It's the same as if, okay, top or bottom. We say, we choose. We had two things, two choices, and we made the right decision. Well, now we just have 4 choices. We're still going to make the best decision. Where do you want to make cation at? Here, 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 here. Left bottom. Right here? Why would you like to make cation there? Right. What if you made it here? How about there? It's the same thing. You'll make cation in the best place. Hopefully you will be rewarded by doing that in terms of your mechanistic pathway. What? Well, you could be doing a mechanism where you had to react the other alkenes. Because maybe I could ask you to give a mechanism for a very minor product that went against, okay? So let's do here. And hopefully, again, that will take us down the road to the right. Get us there. If we see we're heading down the wrong road, maybe we back up and go down another road. Okay? H+. Already got it there. We're going to pull away from this carbon, right? And we're going to get H here. I'm going to go ahead and draw this. Well, no. Let's do it the same way. Then we'll redraw it. Is that it when it reacts? Okay. Now, I- could add here. That could be a possible product, but that ain't that product. Our goal is to give a mechanism for that product. So what can happen instead of I- adding there? Do you think this is going to want to do a carbo-cation rearrangement? It's already tertiary. I mean, I could do a hydride shift from here, and that would create a secondary. That's not good, though. Why would I? Things are not going to rearrange to go to a worse cation. What can attack here? The other alkene. Can an alkene attack a cation? Yes, that's what I did right there. Alkene attacked a cation. That was just a hydrogen cation. This is a carbon cation. Yes. This attacks here. Can this get close enough to attack?
Sure.
All this has free rotation. Free rotation, free rotation. Right? Can this get close enough to clap hands over here? Yes. Free rotation. Let's redraw this like this. This is a carbon with two methyls. Okay? How about if I stop drawing in the new H? And then we have, here's the cation. From there we have 1, 2, 3, 1, 2, 3. Then the two carbon alkene. 1, 2, 3. Then the two carbon alkene. 1, 2, 3. There we go. That's it with just some. Yes. All right. I'm not going to do an arrow here. This is equal. This is the same thing. Now, these pi bond here. What if the electrons break away and go bond to the cation? By the way, if we did this, where are we going to leave cation here? Top or bottom? Bottom. Electrons pull away from here and go attack up there. Here we go. Boom. The electrons break away from the bottom and boom, go bond to the top. What does this give? Back over here. Which carbon ends up bonding to this carbon up here? A or B? Which one bonds to the carbocation carbon?
B.
Hmm?
B.
No. No, not B. Not B.
A.
A. Here we go. B is down here. I'm A. The electrons break away from B and go bond. This ain't bonded up here. This is bonded up here. The electrons. Here we go. Boom. The bond is between here and here now. A is now bonded. This is A and B of the original alkene. These electrons used to sit between A and B, but they moved up here. Now they're between A and that carbon. A is now bonded to that carbon. You guys got to understand this. This arrow is not saying B is bonding here. This arrow is saying these electrons are being grabbed and pulled away from B. Right? That's what they always mean. These electrons are being pulled away from it right here. If we call this C and D, or whatever you want to call it, which carbon is bonded to the H?
C.
You got to see that. Okay? Which bond did we just make over here? Right there. Right? Where's the cation at over there?
B.
On B, yes. Which, by the way, is the cation we need to get the product, right? If we backed up from the product. Now we're home. What's the, this guy was watching the whole time. Don't use all the ink I'm going to use, but it comes through here and bam. All right, you can redraw it right there. Bam. It attacks. And that's how we get that product. So this reaction has sort of a interesting second step. Instead of the nucleophile attacking here, the other pi bond acted as a nucleophile. Which is going to be faster, I attacking here or internal pi bond attacking here? Internal pi bond. Because the iodine's way over there. You see how far away it was? But the pi bond was right there. All I had to do was do this. All right. So we've seen an alkene attack an H+. Now we've seen an alkene attack a carbon plus. And this was internal. Since it's internal, I made a ring. An intermolecular, I'm sorry, not intermolecular, intramolecular.
Are we ever going to see one that has more than 2 pi bonds? So we would react H plus with the most stable form of the stable carbocation and then have to choose between 2 more pi bonds to form the ring, or?
Well, yes, you can see any of such. I thought you were going to say, and then another alkene attacks this cation.
No, just like when you have like just a regular hydrocarbon.
I'm sure you can handle it.
Not-
I mean, to me, you're saying 125 times 45, then you're saying, well, will we ever have something like 120, add one more digit? You should be able to handle it, right? Right? If you could do 125 times 48, I'm sure you could do 125 times 48. I mean, adding one more digit, it's the same thing. But look at the mechanism for how your body makes cholesterol. The precursor to that has about 4 or 5 alkenes, and they end up all reacting in sort of almost the same reaction to make cholesterol. You can find that. It's sort of called a cascade, because it just keeps on making it, and then another alkene attacks. And before long, you got 4 rings of cholesterol. Look at that.
So we'd have 3 intermediates for that reaction?
They're on the board. This is the same thing, just redrawn.
Okay, so just 2.
It's just 2 intermediates, right? Yeah? Questions? All right, let's look at polymerization. If you take this alkene here, what's the name of this alkene? Name of the alkene, and is it stereogenic? It's called propene, and it's not stereogenic. You might say, well, how about 1 propene? Well, the one's not needed, because there ain't no such thing as 2 propene. If you take propene treated with an acid catalyst, you can get a polymer. The polymer will look like this. First step, same old first step. Alkene attacks H+. Where are we going to leave cation? Left or right? Left. We make this secondary cation. What can attack the cation?
Another proton.
Well, first off, there's got to be a minus here. We need to look at what catalyst, what H+ catalyst we want. What is an example of an H+ catalyst where the anion will not attack?
Yeah. Doesn't fluorine on
HF. Yeah. What's another example? More common.
Sulfuric acid.
These were listed on previous page and explained why these were certain choices. Okay. Acids in which the counter anion, the conjugate base, will never attack as a nucleophile.
H2SO4, H3PO4, and HF.
Yes, there you go. Those are the types of acids that are on here, because we do not want anything to attack here. No anion. What else can attack here, though? What's a polymer definition?
Multiple things.
It keeps reacting with itself over and over. We come in with another alkene. And this, can an alkene attack a carbon plus?
Yeah.
We just did it upstairs, except we did it internally. This is going to be intermolecular. Just another alkene attacks the carbocation. Then you're going to form another carbocation. On left or right?
Left.
Okay? What can attack that carbocation? Another one of these. But guess what? Then you're going to make another carbocation. Please look at that, okay? We'll sum this up, but please do a little bit of looking at that, including how we draw polymers. Okay, should be a section of polymers in your textbook. See some of you in lab